Let's proceed with configuration of partitions by now focusing on swap partitions. And files. Now it's imperative that you have swap space available either in the form of a partition or a file, so that when your operating system exhausts the random access memory, it has a place to go. So swap partitions and or files feature primarily extra virtual RAM for the OS, which also extends to user space applications in the event that you need additional storage in memory, of course, in-memory storage. Then the operating system will swap or page in between swap space, whether it's represented by a file and or partition, in and out of memory. So with that said, how do we make swap space available? First and foremost, we should identify what we currently have available. So one, identify current swap space. And we do so using the swap on command with the -s option. So since we have space on this remote system, Linux CBT Server 4, to provision additional swap, we'll do it here. We'll execute swap on -s. This is one way. Swap on -s enumerates the partitions and or files that constitute swap. So let's just note, enumerates partitions and or files which constitute swap storage. You may optionally use the free command, turn on human readable format so it's easy to follow, to get a sense for how much swap space is available. But the free command doesn't tell you to where that space is allocated. It tells us we have about half a gig worth of swap, but it doesn't tell us that it's a partition versus a file, and which partition. So for that matter, we use swap on. This explicitly tells us where the swap is currently allocated. And then if we use fdisk-L, we'll get a bigger picture, a larger view of where the swap is currently allocated on the system. The primary swap is on the primary hard drive, but now we have a new hard drive, and we'd like to allocate swap here, and perhaps eventually move the swap to the second drive altogether to increase performance, as it stands to reason that if you distribute swap away from where you perform the bulk of your I.O., you're bound to benefit from parallel I.O., or swapping on one drive the second drive versus general I.O., reads and writes on the first drive. So we've got space on the second drive, since only 4 gigs are being used for the home one mount point. So we've got about 6 gigabytes worth of space that we'd like to allocate. And we're going to begin by doubling our random access memory. The general rule of thumb is to double your random access memory, which is where the free command comes in handy, because free tells you how much random access memory you have. This tells us that this particular enterprise system, Linux system, has 503, roughly 512 or half a gigabyte worth of random access memory. So for that we should have swap in the ballpark of about a gigabyte. Now rather than creating a partition that's a gigabyte, we can move forward by adding to the existing swap by simply creating a half a gigabyte swap partition on the new hard drive. So we've identified current swap space, and we know it's half a gigabyte. So step 2, select target drive and provision swap partition. And we'll do so using fdisk. So fdisk dev SDB will propel us into the context of the second hard drive. We can optionally use parted to manipulate the partition table of dev SDB. Either or will work, either or will allow you to create a swap partition. But since we've been mentioning fdisk, let's stick with it as it's the most commonly mentioned tool. So again, fdisk-L tells us what's available. fdisk/dev/SDB allows us to manipulate the partition table of the second SATA drive, which is represented as a SCSI drive. M for help, P to print the partition table, N to create a new partition. You need to determine if it's primary or extended. Now, since this will be the second partition, we'll make it primary to leave us room for another primary partition and then the final extended partition, which houses n number of logical partitions. This will be partition number 2, as partition number 1 is currently in use by the home1 mount point. Notice that we can begin at 500 and end at 1305. So this is the space that's available for creating this partition. FDisk currently has no knowledge of the type of partition that we'd like to create, so it doesn't impose any limits based on what it thinks. It simply tells us the first free and final cylinder available. So we'll begin at 500. Again, there is no law stating that you have to begin at the next contiguous free cylinder. You can begin wherever you'd like. But just to keep things in order and to follow in a sequential, logical fashion, we'll start at cylinder 500, which is the next free cylinder. Contiguously speaking, it is the next free space on the disk. If you think of a disk as a record, you could consider SDB1 to be the first track and SDB2, what we're about to create, to be the second track. So we want the size to be 0.5 gigabyte, so we'll indicate plus 512 megabytes. And then FDisk will perform the calculation necessary to determine the total number of cylinders that are to be used. And when we press P or enter P, we'll see that 500 through 562 cylinders, or numbers 500 through 562, will be used. In other words, 63 cylinders are required to provision 512 megabytes of storage. Notice, however, that the type of the partition is incorrect. It defaults to Linux 83. We need to modify this, so we'll indicate T to change the type for partition number 2, and we'll enter L to list the codes of partitions that are available. And if you scroll up, you'll see that for Linux swap, that the partition type is 82 as opposed to 83. LVM is 8E. So we'll make this partition type 82 and then print, and you'll see that it's now a Linux swap partition, which is also compatible with Solaris. So now we have the right partition type defined, which will allow us an extra 512 megabytes worth of space. But again, just like before, we need to commit the changes to disk. So we selected the target drive and we have provisioned the swap partition. So in here we have indicated new, and it's partition number 2, beginning at cylinder 500, terminating at plus 512 megabytes, but in our case it terminated at cylinder 562. In other words, 63 cylinders are required for 512 megabytes of storage. But we're not done. We also changed the type of the partition. Change type to what we indicated in step G, which is type 82, Linux swap / Solaris partition. Then, last but not least, we must commit the changes to disk using W. So commit changes to disk. And again, this is where the synchronization has to take place, and if there's a problem writing, we need to use part probe. So let's write the changes to disk. This will attempt to write to the partition table. Notice the kernel still uses the old table because, again, the disk is currently mounted, at least a fraction of it, partition SDB1. So as far as the kernel is concerned, it is using the old partition table, which is what we have above in our output, where there is only an SDB1. So the kernel still believes that this is the layout of the disk. This is where part probe, again, a which part probe tells us that it's located in SBIN. You can execute part probe with no options. It will just attempt to synchronize the default hard drive, but if you indicate the specific disk, in this case it's DevSDB, it synchronizes with DevSDB. If you indicate the partition such as DevSDB2, no problems, it synchronizes. Now the kernel knows the new layout of the file system, but again, if for some reason you execute part probe on your system for the disk that you've updated, and it doesn't work. In other words, we'll know momentarily when we attempt to create the swap partition using make swap, then reboot your system and it'll take care of it for you. So step 3 in our swap provisioning process is to create the swap file system. We do so using a utility known as make swap, just like we use make2fs to create the ext3 file system with the -j option turned on. To create a swap file system, we use make swap. We follow that by indicating the location of the partition, the raw partition. So create the swap file system on the raw partition. In this case, that partition is dev sdb2 by indicating make swap space /dev /sdb2. This will attempt to overlay a swap file system on dev sdb2. If all goes well, we then enable swapping as our 4th step, and then the operating system becomes immediately aware of the added space to swap. But again, it doesn't mean that we'll use the space, because if you recall from earlier on when we discussed the free command, if you execute free-m, you'll see how much of swap is in use at any time. So although it's recommended that you double your memory when provisioning swap storage, it doesn't mean that you'll immediately use that swap space. It's all contingent upon how many users are connected and how many applications are running. So the more users, the more applications, the more likelihood your system will have to rely upon swap to provide continuous service. So with that said, let's try to make swap on dev sdb2 by copying the command and pasting it into the shell. Here you see it says it set up swap space of roughly ½ gigabytes using version 1 of the swap software. This means that the partition has been properly provisioned. So this checked out okay, and just like is the case with any Linux command, after it's executed, echo the exit status to be sure that that it is a 0, or it is not a non-zero exit status. If it is 0, it has executed successfully. So with that said, step 4 is to enable swapping. And by that we mean publish the swap partition, or swap space we should say, because swap can be provisioned from a partition or a file. So publish the swap space to the kernel, and that's to the Linux kernel. So currently, if we return to the shell and execute free-m for human readable format, we see that the kernel still thinks that there is ½ gigabyte worth of swap space. We want it to now know that we have additional space, and that's the purpose of enabling swapping, in addition to creating the swap file system. And we'll recap all of this momentarily. So to enable swapping, we execute swap on, the same command which displays the current swap devices, but then we follow that up with either the location of the file system or the swapping file system, or -a to indicate that swap on is to read from FS tab. So if you execute swap on, for example, with no options, you'll see that it has the options HV, AEV, so on and so forth. You can indicate a device directly, but if you want swap on to simply read what's in FS tab, you use the -a option. For now, since we have an updated etcfs tab, let's execute swap on dev sdb2. We'll copy and paste, and then the kernel will attempt to allocate the storage. Again, it's now ½ gig. Now we've executed swap on dev sdb2. Now we'll execute free-m again, and it's been doubled to 1 gigabyte. So we can execute swap on with a partition. This enables swapping for dev sdb2, or on dev sdb2. The next step is to update etcfs tab so that when the system reboots, or if we execute swap on -a, this device, SDB2, will be included in the pool of available swap storage. Before doing so, let's now take a look at our swap report using swap on -s. We now see that there are two devices, SDA6, the first partition, or the sixth partition on the first hard drive, that is, as well as the second partition on the second hard drive. Both are available. There's also a priority set which indicates which swap partition will be used. Now let's nano etcfs tab. We'll find where swap is defined, and we can just place the raw partition here, which is dev sdb2. It's of type swap, defaults, and it isn't to be checked when the system starts. We can even include a comment. Newly created 512 megabyte swap partition. And this will get mounted whenever we reboot the system, or if we turn swapping off and then re-execute swap on-A, it'll be re-enabled. For example, just like you have swap on, you've got swap off. Swap off with no options returns options that are similar to swap on. Swap off, dev sdb2 for example, will turn off swapping on that device, and you can confirm as such by executing swap on-S. You can also further confirm by executing free-m. So let's just note, we've updated etcfs tab. We've included dev sdb2 type swap, defaults, 00, so it's not checked. Swap off, dev sdb2 disables swapping on dev sdb2. Now supposing we want to increase performance, so improve system performance by distributing swapping to dev sdb2. To do so, we need to disable swapping from dev SDA6. So first, swap off dev SDA6. But of course we need to turn on swapping somewhere, so let's label as our first task swap on dev SDA or SDB2. Then the second task will be to turn off swapping on dev SDA6 to be sure that we have some swap space, although we currently are not using it. Let's confirm that this is in use by using swap on-S. Both are in use, dev SDA6, dev SDB2. Now let's turn off swapping on the primary hard drive, which is being used to house the root, home, and boot file systems. The exit status is clean, and now we'll again execute swap on-S. So now swapping is only occurring on the second hard drive on the second partition. Free-m will reveal that there's still roughly half a gig of memory available for swapping, but no longer are we swapping on the primary hard drive. Now back to swap on-A. If you execute swap on-A, it will attempt to turn on swapping on all devices. Notice an error is returned for SDB2 because it's already on. However, if we execute free-m, you'll see that we're back to where we were earlier, and that is if we execute swap on-S, swapping on two devices, SDA6 and SDB2. So let's swap off dev SDA6, then update our etcfs tab. So altogether we need to improve performance, and that's also going to be enabled by disabling. So disable dev SDA6 via etcfs tab. Let's give that a try. We'll search for the first swap instance, and there it is. This is the SDA6 entry. We'll ensure that everything's on the same line. We can even include disable to improve performance. So now we've updated FS tab. Swap on-S shows that only one device, and now when we re-execute swap on-A and re-execute swap on-S, we see only one device available for that purpose. So now when the system reboots, we're guaranteed that swapping will be brought up on the second hard drive, not the first. And this is a way to improve performance. Now we've shown you now how to, or thus far, how to create swapping based on a partition. But it's also possible in Linux, like so many other things, to create swapping based on a file. So we like to show this as well because sometimes it isn't feasible to create a swap partition because you may be out of partition space. You may have used all of your hard drive space for user space and swap partitions and need emergency swap space. So this section we'll call Create Swap Based on File. And again, features include the ability to provision swap space based on a file similar to pagefile.sys in Windows, NT, etc. if you have no available disk space to partition. Doesn't mean you don't have disk space altogether. It just means you don't have free space to partition. So you may have used all of the available space on the hard drive, but within each file system you may have many megabytes or gigabytes available that can be used for a swap file. So that said, it's important to know how to create a swap file and then reference it using swap on. We'll list those two that it doesn't waste partitions. Now with that said, let's show you how it works. We need a task as usual, create swap file. Let's make it 512 megabytes, or half a gig. So to do so, we're going to use the dd command. We'll set an input file of dev0, so it'll write zeros to it. Dev0 is a facility, again, which allows you to write zeros when using conjunction with the dd command. But we need to send dev0 to an output file. dd supports input as well as output, as well as other options such as byte size, and it can do it for a certain count, whatever count specified. So the output file will be equal to somewhere where we have space, and let's just find that space, 512 megabytes. We'll clear screen df-h to see where 512 megs is available. We have that space available in home 1. Home 1 is on the second hard drive, so this is an ideal place to put it. So output file will be /home1, and we'll call it swap file 1. The byte size, we'll set it to 1024, and when you multiply 1024 by a number, you need it to add up to 512 million bytes. That count would be 524,288. So when you multiply this times this, you get roughly half a gigabyte. Open a calculator, try it, you'll see. So to recap, the dd command, which is useful for many things, for sending output based on an input, will be used and will reference dev0. So dev0 will serve as a source of writing information, similar to how we've used sequence to generate n number of numbers, such as 1,000,000, 10,000,000, 1,000, so on and so forth. Dev0, with the help of dd and its byte size and count features, will send the output into a file beneath home1 named swap file 1. The entries will be of size 1024, and it will be repeated 524,288 times, consequently making a half a gig file. Once that file has been created, we'll use make swap and then swap on, and then that's it. So let's create that file. Again, you need to identify where free space is available. Now this takes a little while to write the half a gigabyte file, so we just have to wait it out. But if you have another shell open, you can confirm as the file is being written to the hard drive that it's indeed doing what it's supposed to do. Again, dd is just that facility which allows you to take an input such as dev0, but it doesn't have to be dev0. You can take an input of a file and send it as output to some other facility or some other file. So here we see 524,288 records in and out, totaling 537 megabytes. Slightly larger, but it's in the ballpark of what we want. DD also returns the amount of time the process took, just under 25 seconds. It also returns the bandwidth. This is the disk-based bandwidth of 21.5 megabytes that is, per second. Multiply this by 8, and in network terminology, that's about 160 plus megabits per second. So it's really fast. Let's confirm that the file exists using lsltrh home1 swap file 1. There it is. Now if you're concerned about what the file looks like internally, less home1 swap file 1, and it tells you it's binary. So there's nothing much we can do with it. Now we need to turn on the file system, the swap file system. So step 2, which we'll list as B, is to execute make swap followed by the path to the swap file, which is home1 swap file 1. This overlays the swap file system in this file. So just like we did before, if we recap the earlier steps, we enabled swapping using a partition by creating the partition, then using make swap to overlay the swap file system, then using swap on to turn on swapping. Similar process. This is just a file instead of a partition. So let's go ahead and make swap, and there it is. It's set up swap space on the file just like that. The exit status returned is a success. It's a 0 value. So let's move on to the next step, which is to turn on swapping as far as the kernel is concerned. So make swap overlays swap file system. The next step, swap on, followed by the full path to the file, makes swap space available to the kernel. Now before we enable swapping, let's confirm the existing swap space. Free-m is one way to do it. This tells us that there's about half a gig of swap. Swap on-s reports on the devices that currently constitute swap. So SDB2 is the lone device. Now we're going to throw a file into the pool by using swap on home1 swap file 1. We'll echo the exit status. It looks good. And then we'll re-execute swap on-s. Now we see that in addition to dev SDB2, beneath home1, which is indeed mounted on dev SDB1, there's a file named swap file 1, which is also roughly half a gigabyte. Thrown into the pool of things, if we execute free-m, we'll see we now have about a gigabyte worth of swap space available. And we can keep adding swap space. Free tells us whether or not the operating system is using it. Currently, the OS is using almost 100% of its random access memory, which is a good thing. This means most of its work is occurring within RAM. But inevitably, as more users or as more processes or more processes are launched on the system, the kernel will be forced to resort to virtual memory to page in and out items from random access memory. And it does so using a variety of algorithms, but nonetheless, it will at some point need the space, which is why we need to ensure that enough swap space is available. So again, we now have a file and a partition. We also need to ensure that when the system reboots, this swap file is made available. So task 2 is to ensure that when the system reboots, the swap file is made available to the kernel. And to do so, as you may have guessed, we'll simply nano etc fs tab. But the syntax is slightly different. In there we'll place the path to the swap file, which is home1 swap file 1, and be sure to do so after the mount of the home1 partition, followed by the same options, swap, swap, defaults, 0, 0. This is what will be placed into the file. So with that said, let's take a look at the etcfs tab file. We'll clear screen here, reset the buffer, then nano etcfs tab, and also this will help if we execute swap on -a. Again, you want the swap space to be made available after the mount of home1. Otherwise, the boot up process will be unable to find home1 and the swap file. So again, full path, home1, swap file 1, type swap, defaults, 0, 0. That's all that's required. And we'll include a comment that this is an additional 512 megs swap file, and it's located in the home1 mount point. So let's save the changes, and we misspell swap file, so let's go ahead and just fix that. Otherwise, when the system reboots, it will throw an error trying to make the swap space available. Now let's take a look at that swap space again using swap on S. We'll turn off swapping on the file using swap off, swap file 1, echo the exit status, then rerun swap on -s followed by freem, and we're back to about 500 megs. Now we'll execute swap on -a to force a read of the etcfs tab file, and it throws a device or resource busy because the existing partition is in use. However, now when we execute freem, you see that we're back to a gig worth of swap space, and swap on -s will confirm as such, which means, again, if you execute swap on -a and it mounts your swap space, it means when your system reboots, it will mount it for you. Now just a quick note about the two columns we haven't discussed, used and priority. Used reflects what you'd see when you execute free-m. When we executed it, 0 was being used, or 0 bytes of the roughly a gigabyte were being used. So that's self-explanatory. Of each swap point or swap space, whether file or partition, you'll see how much is used. Priority ranges from low to high based on values that are low to high. So it matches accordingly, which means a higher value has a higher priority. -3 is a greater value than -6. So the operating system is more inclined to swap using a partition as opposed to a file. You can influence the priority if for some reason you think, let's say, the file would be faster. Using swap on -help, you'll see how you can influence the priority using -p to turn on a given priority. So for example, let's swap off home1, swap file 1, and then we execute swap on -s. Now we turn on swapping using home1, swap file 1, but we want the priority to, let's say, be 10, which is a greater value than -3. Now when we execute swap on -s, which is in our history, you'll see that the OS is more inclined to use swap file 1 as opposed to SDB2 because we've influenced the priority. The OS by default will choose what it thinks is the faster option, which generally is a partition over a file, when allocating virtual memory. So we've set up our system to reboot and start with swap space. We know how to define a swap based on a file as well as a partition. It's very straightforward, nothing much to it. Just know that the process is the following. If you're creating a file, use DD with the dev0 interface or the dev0 facility. Set your byte size to 1024 and then just multiply it out until you get the size that you like. So if you wanted a 1 gigabyte swap file, just indicate a count that would reflect as much. Or you could indicate count 2 gigs and it does it as well. For example, let's just show you briefly how to create a 2 gig file using DF, or DD that is. So task 3, create 2 GB swap file. Taking the recently used command, instead of indicating byte size, we'll just tell the count to be 2 gigabytes using 2G, and then execute this from the shell. But we'll call this one swap file 2, of course. We don't want to overwrite or risk clobbering the existing file. And providing there's enough space, which there should be, in home 1, we'll create momentarily a 2 gigabyte file. And you can watch a file grow by opening another shell to the server. And this will create a 2 gig file. So you could say count equals 2G or count equals 512M, and you'll achieve the same result. Or you can multiply byte size times count and end up with an appropriately sized file. Once you have that file, enable swapping or provision the file as a swap file. Last but not least, enable swapping in the kernel by using swap on. And to recap a partition, use fdisk or parted to set up the partition. Type 82 Linux of a size that makes sense, 512 megs, a gig, so on. Make swap to overlay the swap file system to denote that it's a swap partition. Then make the swap space available to the kernel by using swap on. And then of course update etcfs tab so when the system reboots it will auto mount the swap space for you. Let's see where we are with this 2 gigabyte file. It's still creating it, and if we were to SSH from a separate shell to 75.199, we'll navigate to home 1 and then lsrth. You'll see the file as it's growing. We could even watch it grow using the watch command, which is another neat program we've neglected to mention. So for example, watch lsltrh swap file 2 will update every 2 seconds, which will reflect changes in the file. So add watch to your list of important Linux commands. It allows you to run the command on your interval. It defaults to 2 seconds, but we can change the default. It's a great utility to watch, let's say for example, the appending of information to a log file. So watch space tail space the file name will cause tail to be refreshed every 2 seconds. And here we see the files being written, 2 gigabytes, and it should stop growing, and in the process in the background will momentarily stop. It appears to be a little bit bigger, but it will stop momentarily and we'll have access to our file. So that said, we'll just go ahead and kill this process, the watch. This will be done momentarily. And if we wanted, we could kill this at this particular stage, and the file still could be used as a swap file. So let's go ahead and kill it. It's wrapping up anyway, and it tells you it made it up to this size, and it'll be done momentarily. Performed at a rate of 17 megabytes per second. So that file can be provisioned as a large swap file as well. So we've covered swapping as well as basic file system allocation. It's really straightforward, nothing major to it.